So while the Arrhenius definition of acids and bases worked pretty well for a while, some further investigation found that some materials behaved like acids and bases when they were not in an aqueous solution. That is, they behaved like acids and bases outside of water. So later in 1923, two chemists by the name of Bronsted and Lowry expanded the definition to be any molecule or an ion that is a proton donor. Now, because some Arrhenius acids and bases, or all Arrhenius acids and bases, rather, give up a H plus ion, which is just a hydrogen without an electron around it, and therefore a lone proton, all Arrhenius acids and bases are also Bronsted-Lowry acids and bases, and these are both aqueous. However, some acids, including hydrochloric acid, when dissolved in things other than water, will also donate a proton. For example, they will donate a proton to ammonia to make it ammonium, leaving behind a chlorine ion. And this all happens, without water. But the Arrhenius definition of an acid and base requires an aqueous solution. So they had to revise the definition. Here I have drawn out both those reactions with the corresponding Lewis dot structures, and you can see the hydrogen, which in this instance becomes a lone proton, joining both the ammonia to become ammonium and the water to become hydronium. And in both instances, it is acting as a Bronsted-Lowry acid. However, in the top instance, where it is dissolved in water, it is also acting according to the Arrhenius definition, because it is in an aqueous solution. What's interesting is that water too can act as a Bronsted-Lowry acid, and this is because, let's say when you mix it with ammonia, it can give up one of its hydrogens. In this case, it's the one I've put in green, and this will become a lone proton, leaving behind its corresponding electron right here. And you'll notice over here the oxygen still has all 8 electrons where it retained the one from the hydrogen. So this hydrogen becomes a lone proton, and it is then able to attach onto an area within the ammonium, and because there's then one more proton than there are electrons, you get a positive ammonium ion and a negative hydroxide ion. Moving on now, the definition of a Bronsted-Lowry base is anything that accepts an H plus ion or just a proton, if you're strictly speaking. In this example, the Bronsted-Lowry base would be this ammonia right here, because it takes on this lone proton to become the positive ammonium. Now, when you have Arrhenius bases like NaOH, you may say that they are Bronsted-Lowry bases because eventually they will take on this H plus ion to form water. But really what's happening is that the NaOH is breaking up into positive sodium and a negative hydroxide ion in solution, and the OH is what joins with the positive hydrogen to yield neutral water. So sodium hydroxide, NaOH, strictly speaking, would not be a Bronsted-Lowry base. However, the OH ion that it gives off right here would indeed be a Bronsted-Lowry base because it accepts the lone proton to become neutral water. So in the case of the reaction we have written here, the water right here and the H2O and the chemical formula would be the Bronsted-Lowry acid because it gives up this hydrogen, which you can see over here on the product side, joins onto the ammonium. Now, the ammonia would be the Bronsted-Lowry base because before it only has 3 hydrogens and then it accepts this lone proton to become ammonium. So remember, Bronsted-Lowry acids are what donate H plus ions, and Bronsted-Lowry bases are what receive the H plus ions. And very unimaginatively, this whole reaction up here is what is known as a Bronsted-Lowry acid-base reaction. Now we also split up acids based on how many H plus or protons they can donate to a solution. And as you may have guessed, the monoprotic acids, that is one proton acids, only donate one proton. So, for example, hydrogen chloride only has one hydrogen, so it can only give up the one hydrogen. It's the same thing with, let's say, nitric acid, where it only has the one hydrogen to give up. Once the hydrogen chloride has gone into solution, it is completely dissolved into its constituent ions. So there's nothing more it can donate. It's already left with solely a chlorine ion, and it's already given its proton to form the hydronium ion over here. Now, polyprotic ions, as you may have already guessed, are ions that give up more than one proton in solution. So some examples would be sulfuric acid, H2SO4, and phosphoric acid, which is H3PO4. And as you can see, both of these have more than one hydrogen ion or proton that they can give up in solution. However, it's not as simple as, giving up two H plus ions and being done. Because H2SO4 is a strong acid, it first will dissolve to completely ionize everything. So when you put it in a solution of water, you will get hydronium and negative hydrogen sulfate ion. Then, once it's completed this reaction fully, it will move on so that the hydrogen sulfate ion and the water will mix to form more hydronium ions and a fully separated sulfate ion, which has a -2 charge on it. However, this -2 charge is pretty attractive to free protons, so what ends up happening is often the sulfate will regain a proton to become hydrogen sulfate again, which is why this is a reversible reaction. However, at any point in time, you will be able to find hydronium, hydrogen sulfate, and pure sulfate within the solution. And as you may have guessed, the hydrogen sulfate goes through this process twice because it has two protons it can give up. So the phosphoric acid will go through this process 3 times, with the phosphate group becoming more and more ionized each time until it eventually becomes a bare PO4 with a -3 charge on it. So getting even more broad from the Arrhenius and Bronsted-Lowry definition of acids, Lewis acids are any atoms or ions that accept an electron pair to form some sort of covalent bond. So in this case, the Lewis acid would be this lone proton, which would also be a Bronsted-Lowry acid, and it would join via this electron pair right here. It would join the ammonia to become positive ammonium, and you can see it joins this electron pair to form what is a bond illustrated by this dash right here. However, a Lewis acid and base don't need to involve hydrogen. For example, barium trifluoride, which I'll draw as a barium surrounded by 3 fluorines, and you can imagine that they have, the dots linking them, will join with a negative fluorine ion and accept this electron pair so that the boron is then completely surrounded to yield barium tetrafluoride, which is negative. As you can see, you have the 1 negative here and the 1 negative here to balance it out. So in this case, the barium trifluoride acts really well as a Lewis acid. It takes the pair of electrons bonded to the fluorine over here
pulls them over, and then becomes barium tetrafluoride, some set up somewhat like I've illustrated there. And just to label the parts of this reaction, because this hydrogen or proton accepts the electron pair right here, this hydrogen atom, or hydrogen cation rather, would be what is known as the Lewis acid. Likewise, because the ammonia gives up its electron pair, it would be the Lewis base. And because this is a transfer of electron pair reaction to form the covalent bond right here, this all is what would be known as a Lewis acid-base reaction, in which the base surrenders its electron pair to the Lewis acid, which in turn accepts the electron pair to form this covalent bond right here. Now, any given compound can fit these definitions a variety of ways. Ammonia, for example, is an Arrhenius acid because when you add it to a solution, it increases the concentration of hydroxide in the solution according to this equation. However, it's also a Bronsted-Lowry base because it accepts the lone proton when you put it in solution. And finally, it is, among both of those, a Lewis base as well because it gives up this electron pair and shares it with, in this case, the lone proton, the hydrogen plus ion.